Probability density function. So events where sample spaces are countable, let's say throwing a die to toss a coin, right, where the outcomes are head and tail, and here 1 2 3 4 5 6. So here we know for a die there are only 6 outcomes, and for a coin there are only 2 outcomes, head and tail. And also the outcomes will be always 1 or 2 or 3 or 4 or 5 or 6. It will never be 2.78 or 4.16, right? It will always be like it has a fixed outcome. We represent it using discrete random variables. Similarly here also it's head or tail. It's never 1.5 head. Okay, it's never 1.2 tail, right? Let's say here we have like 3 or 4 coins also. So there will be either 4 heads or 2 tails or 3 heads, but it will never be 3.1 head, right? So you may check out the cards for the video I did on random variables, right? Now for continuous variables, events such as height of all males in the city, it can be 143.278 centimeter, it can be 160.729 centimeter, and so the values are, so such values we know are they make continuous random variables. Okay, we evaluate them as continuous random variables because of their values. Like they can have a range of values. Okay, so here we determine probability only using a range, right? So let's say x is a random variable. So let's say x is a random variable representing a height of all the males in the city. So the probability will always be determined between 160 centimeter to 172 centimeter, right? The probability will always be for a range of value in continuous random variable, or it can be x less than 160 centimeter, x greater than 172 centimeter, or x greater than 165, right? So we always consider value for a range of values here. However, for continuous random variable, we can never find the probability for x is equals to 164.0 centimeter. The probability for such a value will always be 0. Why? Because a value can never be because the value will never be exactly 164.0, right? Why? Because it will always have some value. Let's say it is 164.000000000. It will always have some value after that, right? So the probability for finding exactly 164 centimeter in a continuous random variable is 0, right? Is almost 0, and the probability is so less that we take it as 0, right? So probability in terms of a continuous random variable will always be evaluated for a range of values, that we can determine the probability of continuous random variables. So for example, probability of lifetime of a security system can be given as by a probability density function equals to, let's say, 3x 20 minus x by 4000, where x can be from 10 to 20, or 20 minus x by 4000. X can be from 0 to 10, or 0 otherwise. Right? Now, if you're asked to find what is the probability uh, that a security system will last between 5 to 7 years, right? So for 5 to 7 years, you have to integrate this function from 5 to 7, right? In terms of graph or a curve, we find the area between 5 to 7, and I just told you that to find the probability for an exact value is not possible. So let's say I want to find what's the probability that the security system will last for 6 years, so 6 years, exactly 6 years is not possible, because it can be 6.001 years, because it can last for 6 years and 1 second, 6 years or 1 minute, 6 years for half a second, 6 years for 1/4 a second. It can never be exactly 6 years. So in terms of graph also, to find an area exactly at 6 is almost a is almost a is almost a negligible value, right? But for 5 to 7 years, we have a value which we can find using integration, and that's what we do to find probability of a continuous random variable using probability density function. Similarly, here also for probability density function from minus infinity to infinity f of x dx is equal to 1, because what does this stand for? It stands for the area under curve from minus infinity to plus infinity. That means the full area of the curve, which will be equal to 1. The similar way, just the way we have it for discrete random variables, the sum of probability is equal to 0. So for continuous random variable, it's probability density function, and for discrete random variables also, it's actually probability mass function. So let's say if I have to plot the graph for the probability of sum of numbers occurring when two dice are thrown. So the possible sum are 2, 3, 4 till 12, right? And the probabilities are possible is 0.02, 0.06, 0.08, 0.11, 0.14, 0.16. So that's the distribution we get if we plot the graph for sum of number occurring when two die are thrown, and with their corresponding probabilities, and we never join them, because probabilities here are discrete. Values are discrete here, so the probability exists for 2, right? It doesn't exist for 2.5, it doesn't exist for 3.2, right? It exists for exact values, discrete values, right? So that's how we plot a probability mass function for a discrete random variable. And there is no there is no area under curve, because again the values are discrete. Now let's understand what's cumulative density function. Now, similar to probability density function, we have cumulative density function, which mathematically is an integral of PDF, right? So if we take the integral of PDF, we get CDF, right? So to be precise, in PDF, we were calculating probability for a random variable, for a random continuous variable x, from a range A to B, right? In CDF, the probability is only is only calculated from the probability is only the probability is only calculated for less than b or less than c, right? It will never be for a range of value, right? It will always be for less than b or less than c values, right? And if we analyze this in terms of math, CDF is f of x equal to minus infinity to x f of t dt, okay, where f of t is a probability density function. Just the difference is that we are calculating the value from minus infinity till x, right? So we are calculating the values for t less than equal to x, right? It will never be for a range of values. And please note that f is a right continuous non-decreasing function here, and we are always finding the probability for less than a particular value, okay, less than c, less than d, right? It's always for less than value, and this is the mathematical interpretation of a cumulative density function.